Hi everyone, my name is Pedro Moraes. I work at the São Paulo University. I would like to thank the organizers for this opportunity of talking about dark matter today. Actually, I will talk about dark matter, Bose-Einstein condensate, and rotation curves of galaxies. The name of the presentation is Modeling Dark Matter Halos with Nonlinear Field Theories. It is a work in progress that I have been developing with some collaborators of mine from different institutions. Well, everyone knows that dark matter is one of the most important open problems in physics, such as dark energy, Graham unification, and well, dark matter does not interact with electromagnetism. Therefore, it cannot be seen. However, its gravitational effects are essential to explain, for example, the structure formation. And by structure, I mean galaxies, clusters of galaxies, etc. And dark matter is also essential to explain the dynamics of galaxies. In particular, it is important to explain the spiral and dwarf galaxies' rotation curves. What happens in the sense of galaxy rotation curves is the following. When one applies the classical Newtonian gravity to study the circular velocity of stars around the center of their host galaxies, one obtains this red curve in this figure. Okay, so one predicts that as one steps away from the center of the galaxy, after attaining a maximum velocity, the velocity should decrease as one keeps stepping away from the center of the galaxy. However, what one observes is that after attaining this maximum, the velocity remains approximately constant. So in order to match theory with observation, one needs to assume that there is a dark matter halo in the galaxy. And this dark matter halo will, of course, increase the mass of the galaxy and therefore increase the circular velocity of stars in the galaxy. So you can match theory with observation. Well, in this sense, dark matter works pretty fine. However, we don't know exactly what it is. Actually, there is a plethora of dark matter particle candidates, such as axions, sterile neutrinos, WIMPs, which are weakly interactive massive particles, among others. Among these candidates, we can quote the Bose-Einstein condensate. The Bose-Einstein condensate is a scalar field model for dark matter. In this model, the nature of dark matter is determined by a fundamental scalar field. And this scalar field is endowed with a scalar potential. So the Bose-Einstein condensate is a scalar field model for dark matter. In this context, dark matter halos can be described as a condensate made up of ultralight bosons. It is really important to remark that recently the Bose-Einstein condensate was observed in the Cold Atom Laboratory, which is orbiting Earth on board the International Space Station. This has been reported in this article published in Nature. Okay, it is a quite interesting article. What happened there is that the microgravity environment of this experiment allow for the observation of the Bose-Einstein condensate during approximately 1 second instead of the millisecond time scale, which was the case for previous ground experiments. Well, the continuous and increasing observations of the Bose-Einstein condensate will naturally allow for the understanding of its viability as a dark matter candidate. What is our goal here? Our goal is to construct a dark matter model based on the Bose-Einstein condensate, which we call is a scalar field dark matter model, sorry. And from this model, from this formalism, from this construction, we will check if it is possible to match theory with observation. So we will construct a dark matter model based on the Bose-Einstein condensate and try to match the theoretical predictions of this model with observational data, especially regarding the rotation curves of galaxies, okay? So in order to do so, this is our framework. Those are the 10 most important equations of our model. We start from equation 1, which is a total action, which depends on the scalar field psi, okay? And we consider this field psi to be complex as equation 2. So we can use this real and imaginary parts of this field psi to write the effective equation as the effective action as equation 3, okay? So effectively, what we have is a two-scalar field model in which the fields phi and chi are both real. If we apply the variational principle to equation 3, if we vary this action with respect to the metric, we obtain equation 4, which are nothing but the Einstein's field equations. In equation 4, the energy momentum tensor is given by equation 5, and the matter Lagrangian by equation 6. We can also vary action 3 with respect to the fields in order to obtain the equations of motion, which in this case are given in equations 7 and 8. The notations here are that V with the subscript phi and the subscript chi are the derivatives of the potentials with respect to the fields, okay? Moreover, since we are working with a galaxy, we can consider spherically symmetric metric. So we can use the metric presented in equation 9. And moreover, we assume the energy momentum tensor to be the one given in equation 10 in terms of the energy density, of the radial pressure, and of the perpendicular pressure. Well, by working with these equations, we obtain this new set of equations. Equations 11 and 12 are the non-null components of the Einstein's field equations for the metric and energy momentum tensor presented previously. And equations 13 and 14 are the equations of motion of the scalar fields. In this new set of equations, a prime indicates a derivative with respect to r, the radial coordinate, and a dot represents a time derivative. So what we need now is to obtain solutions for our scalar fields, okay? Of course, our model will have an equation for the circular velocity of stars around the center of the galaxy. And this equation for V, for the velocity, will directly depend on the scalar field, will actually depend on the solution for the scalar field. So we need to find the solutions. So in order to do so, our method is the following. We consider the Newtonian approximation, which is also referred to as weak field approximation. In this regime, the metric potentials alpha and beta are small and constants. So we can take these exponentials as 1. By doing so, equations 13 and 14, which were, you remember, the equations of motion of the scalar field, are given now as equations 15 and 16. Okay? Note that we have also neglected the derivatives with respect to t, with respect to the time, since we are considering a static configuration, which works pretty well to our considerations, to our system. Well, we have these equations, these differential equations, which are second order, and we now invoke, or we now assume that our potential is given as an equation 17 in terms of this derivatives of the superpotential. There's a superpotential being invoked. This is actually a method seen in the literature to reduce the order of the differential equation, okay? So by doing so, in fact, we obtain from equations 15 and 16 the first order differential equations 18 and 19, okay? And by manipulating them, we obtain equation 20, which is sometimes referred to as orbit equation. So now everything we need is to know how the field phi depends on chi, so that we can decouple the equations 18 and 19 and become able to solve them. Recall that we need to know the solutions for the fields in order to write, in the end of the day, the formula, the equation for the circular velocity of stars in our model. We choose to work with the superpotential given in equation 21, which has already been applied to cosmology, to condensed matter. It is actually a well-known model and quite useful. And by doing so, we obtain equation 22, which, in order to be solved, we can introduce this new variable, psi, so that we can write equation 23, which has equations 24 and 25 as its solutions, okay, for different regimes, for different values of lambda, which is a free parameter of the model. By substituting psi in these previous equations, we finally obtain equations 26 and 27, and obtain finally the solutions for the scalar fields as given in equations 28 and 29. So now we are able to construct our rotation curves. In possession of the solutions for the scalar fields, we can write the equation for the circular velocity of stars around the center of their host galaxies, and obtain profiles for the rotation curve of our model, of our Bose-Einstein condensate model of dark matter. Well, we begin with equation 30, which is an equation for the circular velocity of stars. This equation depends on the mass, and the mass is given as equation 31, which is an integration of the density. Recall that from the Einstein's equations, we can obtain relations between the energy density rho and the components of the Einstein tensor. And by doing so, we can write our solution for the energy density rho as in equation 32. We actually have obtained the solution. So in possession of equation 32, we simply integrate it to obtain the solution for the mass as equation 33. So now we have an equation for the mass and consequently an equation for the circular velocity. We now can construct our rotation curves and confront them with observation. We actually confront them with the analytical fit obtained by Burke to the observational data of rotation curves of dwarf and spiral galaxies. So the result is the following. The blue line here, the blue curve here is our model, while the orange dashed line is the analytical fit of the observational data. Our model agrees with observation in some sense. We actually obtain results that are good in comparison with some results already presented in the literature, obtained from numerical solutions of these equations of motion, okay? We have also implemented this no formalism with the purpose of obtaining analytical solutions in our case, okay? So we have obtained this blue line solution, which is in a good agreement with observations. And for a different set of the free parameters, we obtain this new curve, okay? It is important here to remark that by manipulating the values of the free parameters involved in our model, we can obtain a better fit, which is actually what we are doing right now, okay? So we have shown that by splitting the complex scalar field into its real and imaginary parts, it is possible to construct a theory, which effectively is a two-field theory, and we have obtained the solutions for these fields from which we have derived the circular velocity of stars around the center of their galaxies in order to obtain the rotation curves of this model, which recall is a Bose-Einstein condensate dark matter model. Our result is in good agreement with the observations. And as I said, it is a work in progress. We are now trying to obtain a better fit to the rotation curves, to the observational data regarding the rotation curves of galaxies, okay? We stress here anyhow that our approach presents this good fit, especially for larger values of R, which is not actually seen in the present literature, okay? From these models that obtain the solutions for the scalar fields from a numerical approach. Recall that everything we have done here is analytical. Well, to finish, I quote Vera Rubin, which has an extreme importance in the study of rotation curves, as I think you all might know. And she said, "We have peered into a new world and have seen that it is more mysterious and more complex than we had imagined. Still more mysteries of the universe remain hidden. Their discovery awaits the adventurous scientists of the future. I like it this way." And so do I. Thank you.